Hello, everyone. Sorry for the delay. So we'll get started with our press conference on improved warnings for natural hazards, a prototype system for Southern California. We have three speakers, and they're going to speak in this order. Yehuda Bock, research geodesist at the Scripps Institution of Oceanography in UC San Diego, La Jolla, California. Mark Jackson, meteorologist in charge at the National Weather Service, Los Angeles, Oxnard, California. And Angelyn Moore, research scientist with NASA JPL, Jet Propulsion Laboratory in Pasadena.
It's not up, you got to go back. Oh, there we go, got it. And one more thing, I'm sorry. All right, good morning, everybody. I want to thank everybody for attending, and thanks to AGU. Thanks to AGU for organizing this event. My name is Yehuda Bock from Scripps Institution of Oceanography. Along with my colleagues Mark Jackson, Noah, and Angelyn Moore at JPL, we will describe a prototype system of improved warnings for natural disasters using enhanced GPS. By adding small, inexpensive sensors used in popular electronic devices to existing precise GPS developed by the geophysical community, we can greatly enhance our response to natural hazards such as earthquakes, tsunamis, severe weather, and flooding. The system is faster, more accurate, more reliable, and more versatile than current practice, and has the unique ability to rapidly assess damage to engineered structures and permanent ground displacement that occur during large earthquakes with high accuracy, and that means by a fraction of an inch. We report today on the first use of the system this past July by NOAA's National Weather Service offices in San Diego and Oxnard, California, to forecast a summer monsoon event and issue accurate and timely flash flood warnings. The system is being applied to other real-world scenarios in Southern California, including monitoring of critical infrastructure such as hospitals and bridges. The goal is to save... I'm sorry.
Okay. Which one?
That's up on this. That's on the screen.
Oh, I see.
Here we go.
Okay. The goal is to save lives during natural hazards, including earthquakes, tsunamis, extreme storms, and flooding. We assess and mitigate damage to infrastructure such as hospitals, tall buildings, and bridges. Warnings derived from our next generation GPS system are made available to emergency personnel, decision makers, and first responders through standard and other communications and protocols and interfaces. Here you see two examples. The 2011 magnitude 9 Great East Japan earthquake and tsunami killed about 20,000 people and caused catastrophic damage to infrastructure. Tsunami warning could have been improved with our next
generation GPS system. Building collapses are the primary cause of fatalities during large earthquakes. The CTV building in New Zealand had experienced a large earthquake several months before the 2011 magnitude 6.1 Christchurch event. Some engineers contend that continuous monitoring of the health of the CTV building after the first event could have saved lives. In Long Beach, California, we are currently working with Caltrans monitoring the 1,500-foot Vincent Thomas Bridge. This is the first welded suspension bridge in Los Angeles Harbor to detect any serious wind and traffic-induced motions as well as seismic motions. No, the other way. The other way. Okay. This way.
One more. There we go. Oh, go back. There we go.
All right. The GPS system was first used in July 2013 by NOAA's National Weather Service offices in San Diego and Oxnard to forecast a summer monsoon and issue accurate flash flood warnings. And that's going to be discussed in more detail by Mark Jackson. The picture here shows flooding across Highway 78 in San Diego County in 2013. Doesn't show the movie either.
Yeah, that's right.
Now, the way the system works is we combine GPS with low-cost, inexpensive sensors. In the first case, we combine the GPS with small, expensive accelerometers, and that provides us with continuous motions of a station, some kind of platform. In the plot on the upper right, you can see the continuous motions that occurred during the Great East Japan earthquake. And you see on the vertical axis, which you'll see that the station moved about 2 meters to the south, and you see the progression of motions. Our system is unique that we can measure the total displacements of the ground, while seismic systems only measure the shaking that occurs during the earthquake. The GPS in the lower part of the graph, the GPS plus the pressure and temperature sensors that are deployed over a network of stations, they provide a continuous map of atmospheric water vapor shown in the slide. We're taking advantage of an existing 550 station real-time network that spans areas of high seismic and tsunami risk in the West Coast. This network is already in place. It cost about $100 million to put in, and we're leveraging the system to upgrade the stations with some of our sensors. You see, you see on the lower right that we've upgraded 17 stations already in the summer of 2013. Those are currently operational. and we hope to extend this density of stations along the western coast of the U.S. in the areas of high seismic risk. The particular network down here is intended to monitor the southern San Andreas fault system, which is overdue for a large earthquake. After a large earthquake, buildings can be damaged, tagged, based on their permanent tilt and displacements. And in this photo that you see, we have GPS sensors with our low-cost sensors on the roof of the building. And you'll see that on the right, that we're able to measure the permanent tilt of the building, which is on the order of 0.16 degrees. A 1 degree tilt would be enough to red tag a building. Coming back to the Great East Japan earthquake, this was significantly underestimated by the traditional seismic methods. They initially estimated the magnitude of the earthquake to be magnitude 7 after 30 seconds, and only after 9 minutes they determined it was a 7.9 earthquake. It took 2.5 hours to finally estimate that it was as large as it was. So our system improves on the traditional seismic monitoring by accurately determining the magnitude of large earthquakes by estimating the ground motions and permanent displacements. This series of plots shows that here is the horizontal eastward direction motion of the station that's close to the coast of Honshu. This is one of the stations closest to the earthquake, and you see about 5-meter displacement to the east. Here in the vertical component, you see a 0.5 meter of drop in the station, the vertical station height. And that was the critical component that caused the tsunami. So you have a quick 0.5 meter drop that then caused the tsunami wave, which took 30 minutes to arrive on the coast. And so our system is able to improve the magnitude determination and could have determined that the magnitude was 9 compared to the actual event that occurred. Like traditional seismic systems, our system can detect the arrival of seismic P waves used in earthquake early warning. The P wave detection is used to predict the arrival and intensity of S waves. The early warning in Japan provided several seconds to several minutes of warning depending on your location with respect to the epicenter. To put this in perspective for Southern California, if there was a large earthquake on the southern San Andreas fault, it would take about 1.5 minutes to 2 to reach Los Angeles. And so within this time period, there's opportunity to issue alerts and to have that made available to emergency providers and then on to the public. Now I'm going to hand over the presentation to Mark Jackson, and he's going to describe in detail the meteorological applications of our system. Mark.
Okay, thank you, Yehuda. If you could put the first slide up there. NOAA is a collaborator with Scripps and NASA on this project, and you might be asking, how do we integrate the earthquake early warning system with the actual forecasting and warning of severe winter storms and flash flooding? And it all comes down to water vapor data and trying to detect that water vapor data. If you go to the next slide. It may be hard to believe, but severe winter storms within Southern California can be extremely damaging, many more times damaging actually than a over 7.0 earthquake on the San Andreas Fault, and as many more times expensive as even Hurricane Katrina on the Gulf Coast of the U.S. And based on historical studies, if you look at 3-day rainfall totals, looking all the way back through multiple decades, and if you put the next graph up there, you will see these red dots represent locations, stations in which they have received over 20 inches of rainfall over the last 50 years or so. And you see the concentration of stations along the Gulf Coast of the U.S., which are typically attributed to tropical systems and hurricanes, and also within California, within Southern California and the Sierra Mountains. So again, we receive tremendous amounts of precipitation within this area, which result in very life-threatening and damaging floods. Next slide. So what we see on this graph on the left-hand side are what are commonly known as atmospheric rivers. Those plots on the left side are 3 different atmospheric river events that depict within the red. Those are the areas of high concentrations of water vapor, atmospheric water vapor, moving across the Pacific. Where you have the purples, that's where you have an extreme concentration of water vapor. These atmospheric rivers, which is a relatively new science thanks to the advent of satellite technology within the 90s, help us detect the amount of water vapor, which in these plots is actually concentrated within about the lower 5,000 feet of the atmosphere, very long streams of moisture, which then interact with the terrain along the west coast in Southern California. And you note, I note there the area within the black, the landmass, that the satellite data, due to technological limitations, is not able to detect the amount of water vapor over the landmass. And also, when you look at the amount of water vapor that's concentrated within this long, narrow stretch of water vapor, it's roughly 7 to 15 times the amount that passes through the mouth of the Mississippi at any one time. So we're talking about extreme amounts of water that are coming into Southern California and the West Coast. So this is an actual animation of an atmospheric river event that occurred back in December of 2010. In this plot, we're actually looking at precipitable water. So the sensor can detect atmospheric water vapor, and that then is translated into precipitable water. Precipitable water is essentially the amount of water that we have available within the atmosphere for precipitation. It's really, that defines the baseline element that meteorologists use to help determine the availability of moisture. It comes down to lift and moisture, and this is that moisture aspect. So what we see here back in 2010 is an atmospheric river. A lot of people like to call it also a Pineapple Express. That's kind of the street term to it. Pouring this water into Southern California. With this event in December of 2010, we did have extreme flooding within Southern California. The San Diego area received, many areas received over 20 inches of rainfall over roughly a 7-day period. So the idea of being able to see this amount of water vapor coming across the Pacific Ocean and being able to forecast that is very important into getting those forecasts within days and even out beyond a week of a degree of some sort of intensity of these storms. But again, I point out that that landmass is white. That's because we can't, the satellite technology is not able to detect that amount of water vapor and hence precipitable water over the landmass. Go to the next slide. Another very important forecasting challenge that we have, especially in Southern California and our desert areas, is flash flooding. And an important aspect of forecasting and warning those flash floods comes down to understanding where that water availability is and how that changes over time. And this is a strong thunderstorm producing flash flooding over Ludlow in Southern California. It can be very deadly, as you saw the previous slide earlier in the presentation that Yehuda showed. There's been actually quite a few fatalities throughout time of vehicles that try to cross water such as that. So it's very important to be able to understand where that moisture is, and develop that situational awareness as a forecaster. It's a very challenging science, the whole warning decision process, and it's an inexact science, and we need everything we can get, including an indication of the amount of water vapor and water in the atmosphere, to help us in our warning decision process, so then we can alert the public and emergency responders and help protect life and property. So this is a map that those yellow stars represent conventional weather balloon sites. So these are sites in which a balloon is launched only 2 times a day with the instrumentation that's detecting temperature and the amount of water in the atmosphere, and depending on where that balloon goes, it's then tracked, and that gives you an indication of the wind speed and direction. Now, the limitations of this is that it's only at most twice per day, and you can see the spatial variability here is not very good. We don't have very many locations. It's a very expensive technology, and with this new project now, with these GPS sensors throughout Southern California, and also the Earth System Research Laboratory in Boulder is also another co-PI of this project. These pink dots are all locations in which we can detect the amount of water vapor in the atmosphere that is updated on a very continuous basis. And if you put the next plot up there, you'll see an example of what we can use within our operations. Not directly, we still have to go to the internet. Within this phase of the project, we are accessing this information on the internet and the web. But what we see in that plot is a plot of precipitable water over time, and this is coming to us continuously. And you can imagine, and Angelyn will show a plot here later that shows how infrequent we'd actually get the water vapor data through conventional weather balloons. So we're getting this type of information throughout all of Southern California, every one of these pink dots, that giving us very up-to-date information in spatial variability of where that moisture is. And it's very important within that warning decision process, as I said earlier. And I'll hand it over to Angelyn, and she will explain how we're using and taking advantage of these GPS sensors out there in the field to actually give us that water information.
Thanks, Mark. And when we talk about monitoring the motion of the ground or a building using GPS, we're using the P, positioning. But you might find it a little more surprising that we're also using GPS to monitor weather hazards. That's because, yes, GPS is a weather instrument. A GPS station fundamentally is measuring the amount of time it takes signals to travel from the GPS satellites to the receiving station on the ground. That travel time is also affected by the amount of moisture in the air. So every time we calculate the position of a GPS station, we're also measuring the water vapor. Now, NASA has invested in collaborative projects between JPL and Scripps over a number of years, developing capabilities in both GPS positioning and water vapor. So it was very natural when we started putting together a project involving real-time seismology using GPS that we would also include a weather hazard product. Using GPS for weather is not new. What's new here is that there are now sufficient number of stations in the Southern California region operating in near real time for us to evaluate the benefit to weather forecasters in getting that situational awareness in developing weather conditions. We had the opportunity this summer to evaluate one of these monsoon events. This is where moisture is coming up into southeastern California from the Gulf of Mexico, and from there it can spread to the west and to the north. It's generally able to cause heavy rainfall and dangerous flash flooding. So what you're looking at on the upper left here is the GPS stations in Southern California monitoring the water vapor during this July 2013 monsoon event. And you'll also see events start to pop up there as the flash flooding occurs. On the upper right is also GPS water vapor for selected stations that are shown in boxes on the map. And you can see how this gives the improved spatial detail of what's going on. The red and black stations experience a sharp rise in water vapor early in the event. So this is the moisture reaching that area from the Gulf of California. And sometime later, the station that's to the northwest in gray has this increase in water vapor, indicating that the monsoonal moisture has now reached that area. And finally, after several days of slow and relatively steady increase, the blue station to the north also reaches an elevated water vapor. Above 35 millimeters in this region is generally where forecasters are looking at the possibility of heavy rainfall and flash flooding. The other data types we have on this animation are rainfall, a weather model, and radar. But what you can notice here is that the only data type that can give nearly continuous water vapor over land is the GPS. Now let's take a closer look at the first couple days of this event, and in particular, the southern border of California. So this is where the forecasters at the San Diego National Weather Service office were first looking for the signs of this monsoon arriving in California. And the instruments they have in the south to do that include weather balloon sites at San Diego and Yuma, marked with open circles and the word SOND. Those are about 150 miles apart, so there's plenty of opportunity for the weather to vary in between those two locations. And the weather balloon data at San Diego, there's a launch every 12 hours. So there was one on the 18th here. It was at a fairly moderate level. But at Yuma, you can see there was an elevated level on the afternoon of July 18th. So this shows us again that the moisture had reached the Yuma area, but had not progressed to the west to San Diego. So it would be 12 hours before another weather balloon launch out of San Diego. And the Yuma launches are irregular. In this case, it was 16 hours later. So during that time, there was no new balloon data for forecasters to refer to understand what was happening with the movement of the water vapor. You can see the GPS data, represented by the lines, is giving them a nearly continuous picture of how that is changing during those many hours. And moreover, the stations in between San Diego and Yuma give them greater spatial detail. The station in red in El Centro has a sharp rise on the 19th and eventually overtakes the water vapor available at Yuma. So this, again, is what's new, the spatial detail, the number of stations to give forecasters the situational awareness in this developing condition. Now we have a couple notes from weather forecaster reports at the time of this event. And they noted that they were able to use the water vapor data in between the balloon launches, and that they were seeing GPS water vapor estimates trend higher, and ultimately, based on this, they elected to issue a flash flood watch. And that was borne out. There were quite a few flood reports. I've noted just two here involving trapped motorists between two flooded locations on a roadway, and another where somebody flagged down a passing battalion chief to tell him about a debris flow on another road. So this is very rewarding for us to see NASA's investment in GPS water vapor provide a very real benefit to the weather forecasters, their ability to maintain situational awareness during this developing event and issue effective and timely warnings. And with that, back to you, Yehuda.
Thanks, Angie. Well, the alerts can be sent out in many ways during a disaster to those who are threatened. And of course, the preparation and education are critical. And in this slide here, in this graphic, just show you that the alert input is what's provided by our system. So our system either determines the displacements of the station or of the structure that it's on. It goes up to a system that then ingests that information, and then it's distributed. You see this distribution cloud to the first responders and also eventually to the public on various means. It could be through smartphones, cell phones, television, etc. These are some of the ongoing monitoring projects. You've heard about the National Weather Service partnership and extreme weather events. We're also working now with Caltrans and Vincent Thomas Bridge in LA Harbor for seismic wind and traffic-induced motions. We have a project with UC San Diego Medical Center providing earthquake early warning. And there they're interested in knowing once the earthquake has happened, they want to be able to turn off, shut down elevators, provide alerts to doctors who are in operating rooms, etc. We're also working with the San Diego Office of Emergency Services, using the system for early warning and assessing structural damage. And all this work is funded by NASA, NSF, by NOAA, and by Caltrans. All right, to summarize our presentation this morning, the real-time information from GPS stations, upgraded with small, inexpensive seismic and meteorological sensors, are made available to emergency personnel, decision makers, and first responders to help mitigate threats to public safety. A prototype early warning system in Southern California warns of threats from national hazards such as earthquakes and extreme weather events, and assesses damage to critical infrastructure. As we heard, the system was first used in July to forecast a summer monsoon event and issue accurate flood warnings, and the technology is now being integrated into other real-world scenarios, including monitoring of critical infrastructure, such as hospital and bridges. We also want to extend the system throughout the western U.S. to deal with the multiple hazards that we encounter. This concludes our presentation, and I'd like to open the floor for questions. Thank you very much.
Alexandra Witzy with Nature. I want to push a bit more on this notion of earthquake early warning. What do you mean exactly by warning? Are you talking about responding after the shaking has actually happened to determine what's happening with the building? Or are you talking about warning in the seconds before the quake, in which case how does this integrate with Shake Alert and what the USGS is doing there?
That's right. The early warning refers to detecting the arrival of P waves, the primary waves. Those are basically informational as far as we're concerned, and we can use those to predict the intensity and the time of arrival of S waves, of the secondary waves. So the idea then is that you have this warning time in order to react, and depending on the application, you react differently. And that's just basically how the system works. Was there any?
USGS.
USGS. The USGS is also working on a system. Their system is based on seismic methods. They're now starting to deploy GPS instruments as well, based a lot on the work that we've done over the last few years. And their system is focused specifically on earthquake early warning. So they're basically preparing for a large earthquake. Now, our system also does that. It performs better for large earthquakes when it's really important, by being able to distinguish between different magnitude earthquakes, which is difficult to do with existing seismic methods.
Hi, Megan Seaver with Earth Magazine. I was just wondering about the scale of the flood forecasts. Like how small, how local are you getting, or is it more of a metro area?
Yeah, differentiate between a flood forecast and flood warning and a flash flood forecast and warning. I mentioned atmospheric rivers. Atmospheric rivers are responsible. They can actually have aspects, they can bring flash flooding and flooding. But with atmospheric rivers, what we're trying to do with this system is to better understand these atmospheric rivers. So as the moisture moves onshore, they can really help shed more light on the structure of these atmospheric rivers that would hopefully then lead to us forecasting these days and maybe multiple days in advance to be able to give responders enough time to prepare for what's going to come on. Flash flood warnings can occur on a very small scale. So we've heard the term situation awareness used multiple times, and that's what it is. Because when you look at flash flooding, it happens on very short time scales, on the matter of minutes. And so we're basing our flash flood warnings right now on once we see the thunderstorm form on radar, and we have an estimation of the amount of precipitation that is falling from that radar, or the amount of precipitation that's falling within a surface-based rain gauge. So we have to go through that warning decision process of issuing that warning, and sometimes it can be a very difficult thing. You don't want to overwarn, because then you have false alarm rates that are high. You tend to create complacency on the public's part, because we can't just warn on every single thunderstorm that's out there. So in the back of our minds, when we have this information from a system like this that we can use to help in that decision-making process and issue a flash flood warning, some cases for a very small basin or stream that we are anticipating will be rising very quickly and have rushing water and could be very deadly. That's that extra piece of information that I was talking about earlier that the forecaster has in their toolbox to make that decision. And hopefully the more accurate decision we make with a timely factor to it, then we can actually generate then that appropriate response from the public.
Okay, I'd like to just expand a little bit on the previous question on comparison to the USGS system. The USGS system is specifically focused on earthquake early warning. Our system can do that, but as you heard today, we can also monitor extreme weather events. We can also use it for structural monitoring. So it's always doing something. It's not just waiting around for a large earthquake, which doesn't happen that often. It's also contributing to these other applications, and that's really a big difference with our system.
We have a question from the web streaming chat. This question is from Pete Spotts at the Christian Science Monitor for Mark. How many sensors are currently available for the water vapor measurements? The pink dots is what he's asking about.
I believe there's over, I'm going to default to Angelyn or Yehuda.
There are dozens of stations that
I believe over 100.
Available.
In California, yeah, it's over 100.
And another important part of this project is that there are other GPS sensors out there. For instance, right in my backyard, not my backyard, but close to work, the city of Oxnard has a GPS instrument at their city offices specifically to monitor that shaking. And so, as Angelyn said earlier, we can take advantage of that instrument that's passing through atmospheric water vapor to give us that water vapor information. So we can really gradually add more sites as they become available, and it's really trying to collect all those to give us the higher spatial density even than what we have now.
And I could add that there are quite a few more GPS sensors in California, but they're not operating in real time yet. So the part that we're talking about that's relevant to weather forecasting is the subset that is near real time. So as communications may be upgraded at other stations, this network could grow.
But I should add that currently we can draw from close to 600 of these real-time stations in the western U.S. So these stations are already built. The investment has already been made. We've started in Southern California upgrading close to 20 of these stations, and we hope to expand it throughout the West Coast. So what we're doing is just upgrading the stations with these inexpensive sensors in order to enhance the current capabilities of the system.
Hi, Stephanie Agburn with Climate Wire. I'm interested in learning about how this might be implemented in places outside of California. And so I was curious from, I think, Mark's perspective, how the data product got integrated into the weather forecaster's sort of system, and if you see that taking a while to get picked up in other places. And also I was just curious about the cost of putting something like this together in other parts of the country.
Well, on your first part of the question in terms of how we actually got it into our operations, a meteorologist, a forecaster, we try to get as much data as we can. And it may not be the most accurate data. We develop our own bias corrections, but you can't have too much data in the forecaster's toolbox. And we've come to a point almost where there's data saturation. But through the collaborations that we have with NASA JPL, with Scripps, through NOAA, Esrel in Boulder, we get that research to operations component going to where once a forecaster catches this information and is able to test it in real time. I mean, there's always sort of this cautious nature that a forecaster at the beginning kind of practices, but once it pulls through, once there's this successful event, which like what we had in July, and when we have our sponsors within the agency, outside the agency, that really help promote this and get this down to the fingertip levels of the forecasters to be able to look at this information, then it just sort of catches on and there's this domino effect. What we ultimately would like to do within this project is to integrate this within our official operational systems. We have what's called the Advanced Weather Information Processing System, or AWIPS for short, and that is our official system that we take in the data, we process it, it's supported from an IT standpoint. That's one aspect of this project that we're looking at. Now, as far as expanding this throughout other parts of the country, other parts of the world, the GPS is taking off, I mean, like wildfire, and it's a matter of, again, having these sponsoring projects that can get it down to the ground level. From a cost standpoint, I'll defer that to either Yehuda or Angelyn, but from my perspective, it's a very inexpensive system. What you're doing is you're leveraging from existing systems that are out there used for multiple applications that, from a weather standpoint, again, it's sort of like, while we're here, let's use the data. We have it, we just have to receive it. Let's get it in near continuous time frames we can use it, and many more applications as what were described earlier to use these instruments.
As I mentioned, we're building on existing infrastructure that you say it cost about $100 million or so to implement these systems. And to give you an idea, the cost of a typical GPS station is on the order of $40,000. Our system, since we're using inexpensive sensors, it's a few $1,000s, less than $5,000, where we can upgrade these stations. And that then considerably improves the utility of these stations. So the large investment's already there. Our investment now is not that expensive, and that's really one of the main points that we want to convey today.
Molly Michelson, Science Today. I know last year we heard here that NOAA was working with the California Department of Water to install atmospheric river monitoring stations along the coast. Is this part of that or a separate program?
It's a separate effort, even though that data, we can also use that data. Now, those are multiple sensor stations that not only will give you information on the amount of atmospheric water vapor, but will also give you information on wind speed and direction, lift. So those stations from Water Resources and through the collaboration of NOAA and the Usgs is really to kind of look at that whole Earth examination of atmospheric rivers. Now, these water vapor sensors certainly, or these GPS sensors that we use to detect the amount of water vapor, certainly have applications, of course, in trying to better understand atmospheric rivers. They're just, again, we're not able to detect wind speed, directions, other components, temperature, things like that, that are within these complete atmospheric river monitoring stations from that project.
I have another question from the web streaming chat. This is from Alicia Chang at the Associated Press. Do you have a seismologist on your team? I'm having a hard time understanding how your system can monitor earthquakes, tsunamis, extreme weather events, buildings. Can you elaborate?
Can you repeat the question?
Directed at the panel.
What was the first part of your question?
Do you have a seismologist on your team? And I'm having a hard time understanding how the system can monitor earthquakes, tsunamis, extreme weather events, and buildings. Can you elaborate?
Yes, we have a seismologist that are on our team at Scripps. We have other researchers that have expertise in seismology. Why is it able to address these different applications? What I mentioned, we're combining these sensors, we're integrating the sensors. The combination of the GPS and the accelerometers allows us to determine accurately the ground displacements during an earthquake. That information can then rapidly be used to determine the magnitude of the earthquake and also determine the details of the fault rupture. That then, in turn, in the Japan event, we were able to determine the subsidence of the stations, the earthquake causes the subsidence of the ocean floor, and from that information we can then model what the expected inundation will be of the tsunami. So using the displacements that we determine, and we can then go through a series of steps in order to rapidly determine the earthquake and also to then forecast the tsunami. The other part of the system is the integration of the GPS and the MET sensors. Now that allows us, as Angie and Mark described, that allows us to determine the amount of water vapor in the atmosphere. And from that, as described in detail, you can then use it for weather forecasts and flooding forecasts. Now, additionally, the system, the GPS device and accelerometers can then be put on a structure. Just like they're put at a station, we put the same exact sensors on a structure. And so during an earthquake, not only do we get an early warning from the network itself, but we're also monitoring the structure as the earthquake occurs. So rather than getting indirect information from the network, we get direct information from the sensors that are on the structure. And so that's how we can do all these things. It's basically the integration of these sensors allow us to do these different applications. If I answered your question?
I believe so. Alicia's not come back with a follow-up question.
Okay.
Actually, I lied. Peter, can I ask a follow-up?
Yeah.
So Alicia does have a follow-up question, which is, are there plans to partner with the USGS on early warning?
We are, in a sense, we are collaborating with them, is that we're sharing data. We're providing each other data. We're communicating with them on what we're doing. And well, hopefully that there'll be more interaction with the USGS. But we are, on some level, we are collaborating through the exchange of data and information.
Hi, I'm Irene Glotz with Reuters. I wanted to just first clarify that to use the system, the timing element of the system for the water vapor does not need any enhancements to the GPS.
It does require a couple of weather sensors, either on-site or nearby, simple weather sensors to monitor the surface pressure and temperature. The combination of the GPS and those two measurements give us the water vapor.
Thanks. And so GPS obviously has been around for a long time, and so have accelerometers. So I'm a little curious why it's taken till summer of 2013 to put this together into a working system.
Well, that's a good question. I think there's several factors involved. First, it took a while to develop, to put out the stations. They've already been done. That was over a 10-year period. There's been a reluctance by seismologists to accept new technologies. It's fair to say. And so based on, I'll give you an example, during the Japan earthquake in 2011, their early warning was based on their seismic sensors. But they also had in place hundreds of GPS sensors that were real-time stations, the real-time producers of data, hundreds of stations, like 1,000 stations altogether. But there's very little communication between the seismologists and the geodesists. And so there's been a reluctance to accept this newer technology, but the Japan event clearly showed that you have to take advantage of the GPS. They had GPS, they didn't take advantage of it. Another factor is that we're at a point where we do have these low-cost sensors. These are sensors that are used in smartphones. They're very, very inexpensive devices. And so we're at a point where we can, that they're available and that we can integrate them for our applications. So it seems very, very straightforward, but it's taken this long in order to arrive at this situation.
Thank you. And then I guess just a quick follow-up to that is I understand the value of having the accelerometers on a building and you can kind of real-time measure the tilt, but I don't live in an earthquake zone, so maybe I'm just being ignorant here, but I don't really see how this is an early warning system, and someone else asked about this before. As far as like advance warning of something, so maybe if you could just clarify a little bit about why you're characterizing for earthquake detection and monitoring, why you are characterizing it as an early warning system.
Right. Well, that's first of all, because it can provide early warning. The innovation here is a combination of the sensors. If you use GPS alone, or you use accelerometers alone, each one has its disadvantages. And by putting them together and merging the data streams in real time, then you get these added benefits, what I mentioned. First, you can differentiate very quickly between magnitude 7, 8, and 9 earthquakes, which isn't possible with seismic instruments, and that was shown in Japan. The second thing is you can also use the GPS and the inexpensive accelerometers. And I'll give you an example. The cost of an observatory-grade accelerometer is something on the order of $10,000. In our system, basically, the accelerometer itself is something like $10. So putting that together allows us to detect the P waves, the first arrival of waves, which is just, for us, is informational. And from that information, then we can predict the timing of the arrival and the intensity of the secondary waves. And so the period between the primary and the secondary waves is the period of the early warning. So there is actually, when you pick up the P wave, and you can't pick up the P wave just with GPS alone. It has to be with GPS plus the accelerometer data. So once you have that, then you can predict when the strong shaking is going to occur. You can also determine what the permanent displacements are. The permanent displacements are very important in order to be able to rapidly model the earthquake and also model a tsunami if there's a risk, if there's danger that there will be a tsunami.
If I could expand on that from the, so I'm the atmospheric person over here that's above ground. These guys are below ground. And, the involvement in the project and really hearing and understanding this early warning aspect of earthquakes. And I do live in earthquake country. I haven't been out here long enough to really experience a major earthquake. But from the idea of the time scale of seconds with an earthquake early warning out to days with the warnings or information for atmospheric rivers is very important to understand. But even seconds can be valuable. That could be enough time to, say, get under a doorway. That could be enough time to secure something very quickly. I mean, it's amazing that the science of earthquake early warning, we're talking about seconds, but in some instances, they could be very valuable seconds. And when we're talking about flash flood warnings, we're talking about trying to attain lead times, which is the time between when you issue the warning and when the time the event occurs, of hours. And sometimes we only can provide a lead time of minutes. And so I think that from my perspective, looking at the earthquake early warning aspect of this, either through the work here or USGS work, I think that you use and you get what you can with that early warning, and sometimes it could be enough to save your life.
Yeah, I'll give you another example. For the situation in Japan in 2011, the earthquake itself took 2.5 minutes until the earthquake ended. Within well, seconds of that, the end of the earthquake, we already knew it was a magnitude 9 earthquake. And at that point, we could then generate a model for the tsunami. The first tsunami waves hit the coast 30 minutes after the earthquake ended. So you had 30 minutes in order to prepare to issue an alert, et cetera, et cetera. And so our system allows us, literally when the earthquake is over, to then start the process of alerting for the tsunami. And since it was underestimated in the actual event, the earthquake magnitude, the subsequent tsunami warning was not accurate either, and it occurred over a much larger area and higher inundation than it would have if it was just a magnitude 7 or 8, as they had initially estimated.
I'm sorry, but we're going to have to end the press conference. Did you have a final remark, Dr. Jackson?
Well, I just wanted to say one thing on the tsunami aspect. The NOAA National Weather Service, the tsunami warnings are issued for the west coast out of Palmer, Alaska, and we actually have a pretty good hold on the timing of tsunamis, but what we really need to be better at is forecasting the amplitude of those tsunamis. And a lot of that gets down to being better at understanding the magnitude of the earthquake that's generating that tsunami. So there is some promise here to be able to get the more accurate estimations of inundation. The timing is pretty good. It's that inundation aspect that we still need more work on.
Okay, well, thank you very much for your presentations. Thank you very much, everyone, for participating. The next press conference is at 10:30, which is in about 25 minutes. It's Science from Juneau's Earth Flyby. So there's a few minutes left for reporters to talk to these panelists if they'd like, but we're going to have to clear out the room in about 10 minutes. Thank you.